The paper titled, Effect of Charged Block Length Mismatch on Double Diblock Polyelectrolyte Complex Micelle Cores, explores the influence of charged block length mismatch on the equilibrium structure of double D-block polyelectrolyte complex micelles, DPCMs. Polyelectrolyte complex micelles are hydrophilic nanoparticles that self-assemble in aqueous environments through associative microphase separation between oppositely charged blocky polyelectrolytes. Previous studies suggested that DPCMs can only be formed from blocky polyelectrolytes with identical charged block lengths, a phenomenon known as chain length recognition. However, this work demonstrates that chain length recognition can be overcome by employing salt annealing to create PCMs at equilibrium. The study investigates the effect of charged block length mismatch on DPCMs by mixing a diverse library of peptide and synthetic charged neutral block polyelectrolytes with varying charged block lengths and chemistries. The authors use a suite of physical characterization tools, including small-angle X-ray scattering, SAXS, dynamic light scattering, DLS, and cryogenic transmission electron microscopy, cryo-TEM, to examine the structure-property relationships of the DPCMs. The results show that DPCM structure-property relationships display a range of values that systematically vary with the charged block lengths and chemical identity of the constituent polyelectrolyte pairings. These relationships cannot be described by generalizable scaling laws. The authors discuss the interdependent growth behavior of the radius, ionic pair aggregation number, and density in the micelle core for different D-block pairings. They propose a potential physical mechanism that leads to this unique behavior. The comparison of the results from DPCMs to the scaling laws developed for single D-block polyelectrolyte complex micelles, SPCMs, reveals that DPCM design schemes reduce the size and aggregation number and restrict their growth as a function of charged block length relative to SPCMs. Understanding these favorable attributes enables the use of a wider array of charged molecular building blocks to anticipate and control the macroscopic properties of micelles in various storage and delivery applications. In conclusion, this study provides insights into the formation and properties of DPCMs and highlights the potential of using charged block length mismatch to modulate the structure and properties of polyelectrolyte complex micelles. Provides a visual representation of the formation of PCMs from mismatched and matched block copolymers and highlights the role of salt annealing in overcoming the limitations of chain length recognition. It also emphasizes the complexity of the structure-property relationships in DPCMs compared to SPCMs. Figure 2 in the scientific paper shows the characterization of polyelectrolyte complex micelles, PCMs, formed by mixing PEOBPLK25 and PEOBP-D-L-D200. The figure includes a cryo-TEM image of the PCMs, which shows the micelle cores. The figure also presents SAXS data and a spheroidal form factor fit that determines the PCM core radius, R core, polydispersity index, PDI, and aspect ratio, AR. DLS measurements are used to obtain the hydrodynamic radius, RH, of the PCMs. The combination of SAXS and DLS allows for the calculation of the corona thickness, H, by subtracting the core radius from the hydrodynamic radius. The results from Figure 2 demonstrate the successful formation of well-defined spheroidal PCMs with compact cores and shell thicknesses ranging from 4 to 15 nanometers. The significance of Figure 2 to the paper is that it provides experimental evidence of the formation and characterization of the PCMs. It confirms the presence of well-defined core shell structures and provides insight into the size and morphology of the micelle cores. This information is important for understanding the self-assembly behavior and properties of the PCMs. Additionally, the results from Figure 2 contribute to the discussion of the interdependent growth behavior of the PCM cores, as described in the paper. Figure 3 in the scientific paper titled, Effect of Charged Block Length Mismatch on Double Diblock Polyelectrolyte Complex Micelle Cores, shows the relationship between the core radius of double D-block polyelectrolyte complex micelles, DPCMs, and the charged block lengths of the constituent polyelectrolytes. The figure presents three separate datasets, each representing a different polyelectrolyte pairing, Kd, Ve, Vd. The x-axis of the figure represents the charged block length, while the y-axis represents the core radius of the DPCMs. The data points are color-coded to indicate different polyelectrolyte pairings and are fitted with power law curves. The figure includes both anionic and cationic frames of reference, where one charged block length is held constant while the other is varied. The significance of Figure 3 is that it demonstrates the interdependent growth behavior of DPCM cores as a function of charged block length mismatch. The data show that larger charged block lengths lead to increased core size in all sets of DPCMs. However, the growth rate is not constant and varies depending on the specific polyelectrolyte pairing and the frame of reference. This interdependent growth behavior suggests that the charged block length of one polyelectrolyte affects the ability of the other polyelectrolyte to contribute to core growth. This unique behavior cannot be described by generalizable scaling laws. The results of Figure 3 have implications for the design of polyelectrolyte complex micelles and their applications. The understanding of interdependent growth behavior allows for better control and prediction of macroscopic properties of DPCMs, which are important for various storage and delivery applications. This information can also inform the design of charged molecular building blocks for a wider range of applications. Figure 4 in the paper shows the core radius of double D-block polyelectrolyte complex micelles, DPCMs, as a function of the charged block length of the polyelectrolytes. The figure includes data for different pairs of polyelectrolytes, such as PeOBPLK and PeOBP-D, and displays the core radius for each pair as a function of the charged block length of the block that is held constant. The data shows that the core radius increases with increasing charged block length, indicating that longer charged blocks lead to larger micelle cores. The figure also includes power law fits to the data, which describe the relationship between core radius and charged block length for each polyelectrolyte pair. The significance of Figure 4 is that it demonstrates the interdependent growth behavior of DPCM cores with mismatched charged block lengths. The data shows that the growth of the micelle cores depends on both the charged block length of one polyelectrolyte and the charged block length of the other polyelectrolyte in the pair. This interdependence is not observed in single D-block polyelectrolyte complex micelles, SPCMs, and highlights the unique behavior of DPCMs. The results suggest that the growth of DPCM cores is a complex process influenced by the molecular interactions between the charged blocks, and cannot be described by generalizable scaling laws. This understanding of the interdependent growth behavior of DPCMs can inform the design and prediction of the macroscopic properties of these micelles for various applications in storage and delivery. Other figures that could be useful to discuss in relation to Figure 4 are Figure 2, which shows cryo-TEM images of the PCM cores, and Figure 3, which displays the aggregation number of the micelles as a function of the charged block length. These figures provide additional visual and quantitative information about the structure and properties of the DPCMs. Figure 5 in the scientific paper shows the aggregation number, the number of polymers associating within each nanoparticle, as a function of the charged block length for different polyelectrolyte pairings, Kd, Va, and Vd. The data points and power law fits indicate that larger charged block lengths lead to increased aggregation numbers in most cases. However, the relationship between the aggregation number and the charged block length is not linear and varies depending on the polyelectrolyte chemistry. The figure also shows that different polyelectrolyte pairings exhibit unique growth behaviors, suggesting that the charged block length of one polyelectrolyte influences the ability of the other polyelectrolyte to contribute to the aggregation number. Overall, the results demonstrate the interdependent growth behavior of the aggregation number in double D-block polyelectrolyte complex micelles, DPCMs, and highlight the importance of considering the polyelectrolyte chemistry when designing and understanding these structures. The significance of Figure 5 to the paper is that it provides insights into the relationship between the charged block length and the aggregation number in DPCMs, which is crucial for understanding the structure and properties of these nanoscale assemblies. Figure 6 of the paper titled, Effect of Charged Block Length Mismatch on Double Diblock Polyelectrolyte Complex Micelle Cores, shows the relationship between the core radius of double D-block polyelectrolyte complex micelles, DPCMs, and the charged block length of the constituent polyelectrolytes. The figure includes data for 3 different chemically distinct D-block pairings, PEOBPLK and PEOBP, D, L, D, KD, PEOBPVB and PEOBP, D, L, E, VE, and PEOBPVB and PEOBP, D, L, D, VD. The data points in Figure 6 represent the core radius of the DPCMs as a function of the charged block length. Each dataset is divided into two frames of reference. One where the anionic block length is held constant and the cationic block length is varied, and the other where the cationic block length is held constant and the anionic block length is varied. The datasets are fitted with power law functions, and the resulting fits show how the core radius changes as a function of the charged block length. The significance of Figure 6 is that it demonstrates the interdependent growth behavior of the DPCM cores as a function of the charged block length. The power law fits reveal that the growth of the core radius varies systematically with the charged block lengths and chemical identity of the constituent polyelectrolyte pairings. This interdependence suggests that the charged block length of one polyelectrolyte influences the ability of the other polyelectrolyte to contribute to the core growth. The results indicate that DPCMs exhibit unique structure-property relationships that cannot be described by generalizable scaling laws, unlike single Diblock polyelectrolyte complex micelles, SPCMs. The findings have implications for the design and control of DPCMs for various applications, such as storage and drug delivery, by enabling the use of a wider array of charged molecular building blocks. The paper explores the effect of charged block length mismatch on the equilibrium structure of double Diblock polyelectrolyte complex micelles, DPCMs. Previous studies suggested that DPCMs can only form from blocky polyelectrolytes with identical charged block lengths. However, the authors show that chain length recognition can be overcome by using salt annealing to create PCMs at equilibrium. The study examines various pairs of peptide and synthetic charged neutral block polyelectrolytes with different charged block lengths and chemistries. The results reveal that DPCM structure property relationships vary systematically with the charged block lengths and chemical identity of the constituent polyelectrolyte pairings. The growth behavior of the Micelle core, including the radius, ionic pair aggregation number, and density, is interdependent and influenced by the charged block length. The study also compares the results of DPCMs to scaling laws for single D-block polyelectrolyte complex micelles, SPCMs, and finds that DPCMs have smaller core sizes and aggregation numbers, and their growth is restricted compared to SPCMs. Understanding these unique properties and interdependencies allows for the more predictive use of charged molecular building blocks in the design of micelles for various applications in storage and delivery. If you are an author or copyright holder for the work presented in this video and you have any issue with the existence or contents of this video, please let me know.